Hi everybody, welcome back. Today we're going to be looking at lesson 4 in the unit 10, kinetics and equilibrium. And just kind of so you know where we're going with this, kinetics and equilibrium we said is all about how do you manipulate a reaction. And so we looked at kind of just how you picture a reaction with the kinetic molecular theory as particles bouncing around and sometimes running into each other and reacting. And then we started to look more at what makes a reaction just kind of happen naturally on its own when we studied enthalpy. Today we're going to look at Le Chatelier's principle, which is all about how can you make reactions go forwards or backwards. And then in the next lesson, we'll do part 2 of the concept. How can you tell what makes a reaction just sort of naturally happen? And then hopefully all this will make more sense altogether. So today's aim is 10.4. What is Le Chatelier's principle? I'll walk you through the question of the day, then the lesson on equilibrium or Le Chatelier's principle. And then we've got a demo video and optional practice homework number 26. Okay, so question of the day says, what is the change in enthalpy for the reaction above? So the change in enthalpy, or also known as heat of reaction, is potential energy of the products minus potential energy of the reactants. So I'll just write that up here. Just write that up here to remind us. PE products, I'll abbreviate, minus potential energy of the reactants. So for products, looks like got about 350 kilojoules. Reactants, looks like about 200 kilojoules. So that makes positive 150 kilojoules. And I included the positive sign because with enthalpy, you often want to say if it's positive or negative because that really matters. It shows you if it's endothermic or exothermic. Speaking of, question 2, is this reaction exo or endothermic? This is endothermic. One way we can tell is because we have a positive number. Another way we can tell is just looking at the shape of the curve. The products end up with more energy than the reactants started with. So that means overall, this much energy had to be put in to the reaction for it to happen. You had to start with this much energy, activation energy here. Then you got a little bit of energy back out when new bonds were made, but overall the reaction had to absorb that much energy to happen. So the third question, do you think it's more likely to go forwards or backwards? Well, if we look at the forwards reaction, we know it's endothermic. What if it were backwards? Then this would be potential energy of the reactants, this would be the activation energy, and this would be potential energy of the products. The backwards reaction is exothermic. And we know that it's more likely for an exothermic than an endothermic reaction to happen because it can make its own energy and kind of keep itself going potentially. Whereas an endothermic reaction, you have to keep putting energy in to keep making it happen. So I would say the backwards reaction is more likely than the forwards reaction. All right, next we've got answers for homework 25, and you can pause on each slide to look at my notes and answers, and or you can look at the PowerPoint and go as slowly as you like through that. There's more than one answer to C. I put 2 or 4 on number 9. Okay. All right, our lesson today is 10.4. What is Le Chatelier's principle? So the first thing to know is that a reaction can go forwards or backwards. And one of the first people to be known to figure this out was Berthollet in 1803. He was wandering the shores of the Natron Lake in Egypt, and he found these deposits on the shore, and he recognized them to be sodium carbonate. but he knew that calcium carbonate formed in the lake, often from sodium carbonate. So now he saw something that he recognized as a product. It had formed on the edge of the lake, but he previously knew it to be a reactant. So that was an example of a reaction that can actually go forwards or backwards. The full reaction is sodium chloride and calcium carbonate makes sodium carbonate and calcium chloride. And maybe you guys even recognize which type of reaction this is. Yeah, double replacement. And then it can also go backwards. Sodium carbonate and calcium chloride can make sodium chloride and calcium carbonate. So equilibrium, we've talked about a couple times this spring. That's when a forward and a reverse reaction are occurring at the same time and at the exact same rate. So it's like it's going forwards exactly as fast as it's going backwards. So to us humans, it doesn't really look like a reaction is happening anymore. It looks like the reaction is stopped, when in fact it is still going forwards and backwards, but just at exactly the same speed. So here's an example of one that we're going to see a video of later. NO2 turning into N2O4. That reaction can go forwards and backwards, and you can see when it's reached equilibrium because the color stops changing. So when the color stops changing, it's not getting any darker, it's not getting any lighter. It's still reacting to get darker and to get lighter, but at the exact same rate. We'll see that one later. So you can tell something's at equilibrium because you're not getting any more product anymore, or losing any more reactant, or vice versa. The concentrations of the reactants and products remain constant. Okay, does equilibrium mean that there's an equal number of reactants and products? No, not hardly ever. Some reactions go mostly to products and then they kind of slow down and reach equilibrium. Some barely get started, make only a few products, and then they reach equilibrium. So it's not that equilibrium means you have the same number of reactants and products. It means that the amount you have is just staying constant and is no longer changing. So it's not an equal concentration of reactants and products, it's an equal rate of creating reactants as creating products. So equilibrium can be chemical or physical, and we've looked at a couple examples of physical equilibrium this year, but here's an example of a chemical equilibrium. So it's kind of key here, you'll notice that this is in a closed container, because you can't always have a reverse reaction, right? Like if you made a reaction that released hydrogen gas and then the gas went away, you can't really get it back and turn it back into reactants. So not all reactions are going to be go to equilibrium. But in this case, it can. So we've got methane and water vapor in a closed container. So CH4 plus H2O make 3H2 and CO. And that is a reaction that can go backwards as well as forwards because it's all contained in a closed container and the products can turn back into reactants. So imagine that over time, you start to run out of CH4 because it's all turned into products, right? If you start to run out of the CH4, the methane, what do you think would happen to the rate of the reaction? Picture kinetic molecular theory, particles bouncing around. Now fewer and fewer of them are methane. Is it likely to have an effective collision between methane and water if you're running out of methane? No, it's not as likely. So that means fewer and fewer of those reactions will happen as you run out of methane, and so the forward rate of the reaction will slow down. At that point, what do you think is going to start to happen to the rate of the backwards or reverse reaction? If you're running out of methane, that means you have a lot of the products, right? A lot of carbon monoxide and hydrogen gas. So if you have more and more of those, they're bouncing around in this container too. Picture kinetic molecular theory again. Is it likely for them to collide and react? Yeah, it's getting more and more likely for them to collide and have an effective collision and turn back into the reactants. So this is how equilibrium can occur chemically, is that the forward reaction slows down, the reverse reaction starts to speed up until eventually they're the same rate. And at that point, you're at equilibrium. Equilibrium can also be physical. An example is the freezing point. When temperature equals 0 degrees Celsius, we know that's the rate, that's the freezing point of water. It's actually another way of thinking about it is it's where the rate of freezing equals the rate of melting. If you heated this icy waterfall up to 0 degrees Celsius, it would start to melt, right? And if it had all melted and turned into water and you cooled it back down to 0 degrees Celsius, it would start to freeze, right? So 0 degrees Celsius is that temperature where the freezing and the melting are in equal relationship to each other. Just as many particles are going from liquid to solid as are going from solid to liquid. So if you had to take a guess, at what temperature do you think equilibrium between the liquid and the gas phase occurs for water? Right, at 100 degrees Celsius, at boiling. Right at 100 degrees, actually as many particles would be boiling as would be doing the opposite, condensing, turning back into a liquid. Another example of a physical equilibrium we saw this spring was when we studied solutions, and we said a saturated solution, remember that's one that's holding the maximum amount of solute it can. And if you add a little bit more solute in there, maybe it'll dissolve, but that means other particles that had already dissolved in the water will come out of solution and become solid again. So saturated solution is in equilibrium because just as many particles are dissolving as are undissolving. Equal rate. Okay, so Le Chatelier's principle deals with systems at equilibrium. It says that a system will undergo changes to reduce any stress made to the system. So that means any change in temperature, concentration, or pressure. T for temperature, M for concentration or molarity or pressure, to re-achieve equilibrium. Or you can think of it a little bit like this teeter-totter. Okay, at equilibrium, you have a certain concentration of reactants, certain concentration of products. Something happens, maybe you added a bunch more reactants to the system. Ooh, okay, it's not at equilibrium anymore because this is not the equal concentration, the constant concentration that the system had at equilibrium. So it will respond by turning a bunch of reactants into products, speeding up the forward reaction, and then eventually there'll be enough products that the forward reaction and the reverse reaction will be at the same speed again. Now to make this diagram a little bit better, I kind of wish it started off at a tilt because you don't usually have the same number of reactants as products. It's just you have the same rate of reactants turning into products as vice versa. But the other way to think about Le Chatelier's principle is just that a system likes to be at equilibrium. Every reaction has this like sweet spot that it is lowest energy at basically, and it's a certain ratio of products to reactants. So let's consider this system here. We've got carbon dioxide gas is the reactant. Carbon dioxide aqueous is the product. So you can picture a can of soda, right? The gas particles above the soda, and then in the soda, the gas bubbles. All right, what would happen if we added a bunch more CO2 aqueous? If you pumped some more gas into the liquid? Yeah, some of the bubbles would escape, right? So that, in other words, the reaction would speed up in the reverse direction to re-achieve equilibrium. This would be a stress, right? Adding more of a concentration of something is a stress. So the system, according to Le Chatelier's principle, will respond by removing that stress. So if you add a bunch of product, the system will respond by reacting faster in the reverse direction to create more reactant. Or you could say the system shifts to the left. You can say that. That's a way to describe that. Okay, what would cause this system or this reaction to shift to the right and create more product? Well, if you pumped a bunch of gas molecules up here into the gas area, some of them would go down into the liquid, right? So you could add a bunch more of this, and that would shift the reaction or the equilibrium to the right. You could also take away a bunch of the carbon dioxide bubbles that were in the aqueous form, and then that would make some of the ones that are in the gas form go down into the aqueous. That would cause the reaction to shift to the right. If you increased the pressure, increasing the pressure here on these gas bubbles will push more of the gas bubbles into the aqueous form. So increasing the pressure would also shift this system, shift this reaction to the right. Or in other words, speed up the reaction in the forward direction. Yeah? Okay. Let's do another practice problem here. Using Le Chatelier's principle, we're going to consider the following reaction. We've got 2 molecules of hydrogen gas plus 1 molecule of oxygen gas makes 2 molecules of water and a caveman. Just kidding. And heat. That's a picture of heat. Okay. So, by the way, is this reaction endo or exothermic? Exothermic. How can I tell? Heat is a product, right? Or it's producing heat. Heat exits this reaction. Okay, so we're considering this reaction. It's in equilibrium. It's got the double arrow, so we can tell this is a equilibrium reaction. So let's imagine what would happen if we added more hydrogen gas. Picturing kinetic molecular theory, if you add a bunch more H2, now it'll be more likely for this reaction to happen between H2 and O2 because there's a higher chance of hydrogen molecules running into oxygen molecules. So that would speed up the forward reaction, or in other words, shift this system to the right, create more product. What would happen if we added more heat? Well, in this case, heat is a product. So if you add heat, according to Le Chatelier's principle, the system will respond by trying to remove that stress. So adding heat or changing temperature is a stress. So to get rid of the heat, the system will respond by reacting in the reverse direction. So heat and water will react to make H2 and O2. So it'll speed up in the backwards direction. Or in other words, the system will shift to the left if you add heat. What would happen if we increase the temperature? Increasing the temperature is the same as adding heat. So again, the system would respond to remove that stress by shifting to the left. What would happen if we increased the pressure? Well, let's take a look here. Pressure, we know, only affects gases. It doesn't affect liquids or solids. So in this particular reaction, we have gases only on the left side and a liquid on the right side, on the product side. So increasing the pressure would only affect the gases. So let's picture kinetic molecular theory again, particles bouncing around. If you increase the pressure on the hydrogen and the oxygen molecules, now they're going to be more likely to run into each other and have an effective collision. So that will speed up the forward reaction. Or in other words, increasing the pressure would shift this reaction to the right. All right, so here's an example. In a laboratory, 0.1 mole of colorless hydrogen iodide gas at room temperature is placed in a 1 liter flask. The flask is sealed and warmed, causing the HI to start decomposing to H2 and I2. The temperature of the contents of the flask is constant. During this reaction, the contents of the flask change to a pale purple-colored mixture of HI, H2, and I2. So it started off colorless, now it's turning purple. When the color of the mixture in the flask stops changing, the concentration of I2, iodine gas, is determined to be 0.013 moles per liter. The relationship between concentration and time for the reactant products is shown in the graph below. So here's the iodine forming, that's the thing that's purple. Let's take a look at the graph. Okay, so here's the concentration, here's the reactant. Started off with HI, and here's the product. It says each product, so this is the H2 concentration and the I2 concentration. All right, it says state, in terms of concentration, evidence that indicates the system in the flask has reached equilibrium. So how can we tell that this reaction has reached equilibrium? That it is going just as fast in the forward direction as it is in the reverse direction? Well, in terms of concentration, I can tell because the concentration is no longer changing. We started off with 0.1 of the product. Now we have like 0.075, it looks like. 0.075, 0.075. It's not going up, it's not going down. The concentration is constant. Same with the product. We're not getting any more or any less, even though it's still reacting. It's reacting just as fast to make product as it is to make reactant. If this question said, state other evidence that indicates the system has reached equilibrium, we could have noticed that they said the color of the mixture in the flask stopped changing. So if it was starting to get purple and then it stopped getting any more purple, that's another piece of evidence that it reached equilibrium. But they asked for in terms of concentration, so I think this is a better answer for that one. All right. So our last demo here are some really great videos of demos I would have done for you in class if we'd been able to meet there. So I really encourage you to take a look at these videos and really stop and pause the video and make sure you understand what's going on at each step. You can watch it a few times. And I'm not sure if the sound comes through when I do it through this recorded video. So if you can't hear the sound, I encourage you to watch it again following the link in the PowerPoint. So you can just click here. So I'm going to go to the video and play it even though you can't hear it because some of the stuff they write. And then I'll go to the last few slides, which are the optional practice homework number 26. The music is the guy who wrote the Mole song, too.
Stir until it's sweet as it can be. You look down deep. There the
First, we'll observe the effect of changing the concentration on the equilibrium. The equilibrium that we'll study is one of dichromate in equilibrium with chromate ion. Dichromate is orange in solution, while chromate is yellow. We'll observe the effect that adding HCl and adding OH minus will have on the system.
Dynamic equilibrium. Dynamic equilibrium. When the rates of two opposing reactions are the same. Dynamic equilibrium. So let's get back to that coffee cup. Nothing's going on, but wait. At the surface of the sugar, molecules dissolve and recrystallize at the same rate.
In the first example, we added H+, which increased the concentration of the H+ ion in equilibrium. This stress caused the equilibrium to shift left. Next, we added OH-, which reacted with the H+ and lowered the concentration of the H+, causing the equilibrium to shift to the right. Next, we will try to determine if an equilibrium is exothermic or endothermic. The equilibrium we will study is equilibrium with N2O4 in equilibrium with NO2. N2O4 is colorless, while NO2 is brown. We'll observe this equilibrium at 3 different temperatures: at a high temperature, at room temperature, and at a low temperature.
I just want to pause on this screen so you can see these are the 3 beakers. They're putting one on the hot plate is at 90 degrees Celsius. The one not on anything is at room temperature, 20 degrees Celsius. And the one in ice water is going to be at -4. And then I'll pause again when they are in their 3 containers so we can compare or the 2 containers rather, so we can compare the color.
Now the Chatelier had a principle.
Okay, starting to change color. Can you tell which one's getting darker and which one's getting lighter? Okay, that'll be key to figuring this out.
And I don't mean the head of his school. He observed chemical reaction.
As observed by the increased intensity of the brown, increasing the temperature shifted the equilibrium to the right. This means that heat is a reactant, and the equilibrium was shifting to the right in order to use up the excess heat. This was confirmed by the decrease in temperature when the equilibrium shifted to the left, trying to replace the heat that was lost. Therefore, the reaction is endothermic, and the delta H is greater than 0.
All right, so if that didn't quite sink in, feel free to watch that video again so you can see the reason for the color changes. And I did just want to point out the first one they did with the dichromate and chromate. So they added acid to the yellow stuff and it turned orange. Then they added a base and it turned back yellow. Did that remind you of anything we studied in our last unit? Yeah, hopefully it kind of reminded you of an acid-base indicator, right? And actually that's how acid-base indicators work. They're all at equilibrium, and adding an acid or base shifts the equilibrium, and the system responds by changing colors to use up the acid or to use up the hydroxide. Okay, cool. Here is your practice optional homework number 26. And I will just say that if Le Chatelier's principle seems kind of confusing right now, the more you practice it, the easier it gets. And it is going to be a big topic in AP chemistry too. So this is just our first little dip in, and we'll keep practicing it next year. Great. All right, thanks everybody. Have a wonderful rest of your day.